Hello. Today we are going to learn comparison test. There are two comparison tests that we learn in this course, Calc 2. The first comparison test is called direct comparison test that we are going to learn today, and then the next one is called limit comparison test that we are going to learn in the next class. All right. So first of all, let me give you the theorem of direct comparison test. All right. So this is the theorem, direct comparison test. Let an smaller than or equal to bn for all n greater than or equal to 1 if sigma bn, n goes from 1 to infinity, converges then sigma an, n goes from 1 to infinity, converges. Okay, that's the part A of the direct comparison test. This is the part B of the direct comparison test. If n goes from 1 to infinity, an diverges, then sigma bn, n goes from 1 to infinity, diverges. All right, so this is the direct comparison test. This is a very straightforward theorem. Anybody can understand this theorem. Let me explain this theorem a little bit. Here you have an, and then here you have bn. Bn is greater than or equal to an. All right, this happens always. That means for all n greater than or equal to 1. This happens for all n greater than or equal to 1. All right. So then what you do, you just get summation of both sides. So then what you have is sigma n goes from 1 to infinity of an, sigma n goes from 1 to infinity of bn. All right. Now, part A says if bn converges, that means the bigger series converges. If the bigger series converges, the smaller series converge. All right. The bigger series converges means this is the bigger series. The bigger series converges means this is less than infinity. Okay, the sigma bn is less than infinity. Since sigma bn is less than infinity, sigma an is also less than infinity. Okay, sigma an less than infinity means this series converges. That means if this series converges, the larger series converges, the smaller series converges. All right. In the next case, it says sigma an diverges. That means the smaller series diverges. This series diverges. That means this equal to infinity. All right. The smaller series diverges. That means that equals to infinity. That means sigma bn greater than or equal to infinity. Okay. Nothing can be greater to infinity. So the conclusion is sigma bn equals infinity. This says sigma bn greater than or equal to infinity, but the greater than symbol does not work because the infinity sum is infinity is the largest that you would think. So it is sigma bn equal to infinity. That means this bn diverges. Okay, that's part B here. That means if ban diverges, bn diverges. That's part B. Part A is if sigma bn converges, sigma an converges. So that is the direct comparison test, which is a very easy thing to understand. Okay, so let me discuss some other materials since you understood the theorem. So in examples you were given only one series, so you have to create the second series by your own. Okay, you have to generate the second series by your own. Let's talk how to generate the second series. That means the series that you use to compare with. Okay, that's the first bullet. What series the given series compared with? What series the given series is compared with? All right. For that you can use some known series. You have learned a few series so far, which are well-known series. The first well-known series for you is geometric series. Okay, so you have learned geometric series. Okay, you know how to determine convergence and divergence of geometric series. Convergence and divergence of geometric series. And then next thing is telescoping series. All right, so you know how to recognize convergence and divergence of telescoping series too. And third series that you would compare with is the P series. All right, you also learn P series. You know how to compute convergence and divergence of that. All right, you learn P series in the previous section. That is the integral test. You learned integral test last week, so you know the P series. All right, so you could use these series to compare the given series with. Then the next bullet is how to derive the second series. Okay, now let's talk how to derive the second series. Only the first series will be given to you, so you have to derive the second series. How to derive the second series. All right. For that, I would say we might be able to use the following facts. So I'm going to give you some facts that you could use. The first fact is, ln n is always greater than a constant. Okay, and then ln n is always smaller than some n to the power a. Keep that in mind. This a is positive and c is a constant. And c is a constant. The second point, n to the power a is always less than e to the power n. Alright, next thing, e to the power n is always less than factorial n. So you could use these identities to derive the second series. Alright, let's discuss an example so you can understand everything very well. Example number 1. This is the given series to you. Sigma n goes from 1 to infinity, 5 over 2n square plus 4n plus 3. You have to check whether this converges or diverges. Okay, you have to check whether this converges or diverges. Here, first find the nth term. So that is the nth term. That is an 5 over 2n square plus 4n plus 3. Alright, now you have to get the second term. So you would try getting second term like this. What I'm doing is I'm just ignoring these two terms. Let's see what happens if I ignore those two terms. If I ignore those two terms, what I get is 5 over 2 to the power n square. So you can write this symbol for that. Once you eliminate positive terms from the denominator, whatever the remainder is, whatever remaining is actually greater than what you had before. Okay, so this is your Bn. You can assume this as your Bn. Now you have two series, An and Bn. You have An here and you have Bn here. Now think of getting a series out of Bn. That means, let me write that, we have to show that sigma Bn n goes from 1 to infinity, that is sigma n goes from 1 to infinity 5 over 2n square. We have to show that converges. Why this? You have to show this converges. You know, Bn is greater than An. Bn is greater than An. Now you have to show Bn is convergent. You have to show that one is convergent. If this one is convergent, this is convergent. All right. If this one is divergent, you can't tell anything about that. If this is divergent, you can't tell anything about that. That's how the theorem works. If this one divergent, that is divergent. If this one is convergent, you can't tell anything about that. So that's how it works. Okay, that is the given theorem. Alright, so that's the given theorem. See, you have to show this one converges to tell that one converges. You have to show the bigger series converges. The bigger series is this. And now just work on this. This can be written down as 5 over 2 sigma n goes from 1 to infinity, 1 over n to the power 2. Okay, now how about this series? Converges or diverges? Consider sigma n goes from 1 to infinity 1 over n square. Alright, so if you remember, this is a P series. This is a P series. Let me write that like this. This is a P series with P equals 2. Okay, P is the power actually. That power is actually P. Okay, where P equals 2. That means P greater than 1. If P greater than 1, you could say this P series converges. Okay, we have learned this in the previous class. I will show you the note quickly. It was the integral test. At the end of the integral test, I gave you the P series. See? So this is the P series in the previous day note. This is a P series with P equals 2, which is greater than 1. Thus, this series sigma n goes from 1 to infinity n to the power 2 converges. Alright, that means the bigger series converges. Okay, the bigger series converges. That means the small series also converge. Then you could say the small series, which is right here, that converges. Okay, before telling that, let me make a small change here. What I'm going to write is, I'm going to write sigma an, then sigma bn, n goes from 1 to infinity, and this is 5 over 2 sigma n goes from 1 to infinity 1 over n square. You know that converges. Since that converges, everything converges. Okay, since the red part converges, entire green part converges. Thus the conclusion is sigma n goes from 1 to infinity an, which is sigma n goes from 1 to infinity, your an is 5 over 2n square plus 4n plus 2 converges. Okay, by the direct comparison test. That is example number 1. Let's move to example number 2. The example number 2 is this: sigma n goes from 1 to infinity ln n over n. You have to find this is converges or diverges. All right. Now you can find the second series which is greater than this, or the second series is smaller than this. Okay, let me think how to do that. That is the nth term, which is an. Now you have your an like this, ln n over n. Now you can choose the bn such that is greater than an or bn less than an. Alright, so it depends. Let me work on this. So first just try making something greater than that. Okay, so let me make something greater than that. In the previous note, I gave you note like this. See this part? I wrote like n to the power a is greater than ln n. This a can be any positive number. Okay, so let me write this. Let me have small space here. We know ln n is smaller than n to the power 1. Okay, that means n. Okay, so you for this one you could put n over n. What I have done is for ln n I put n. Okay, so that's why we have this greater than symbol. All right. So let me just move this little up. All right, so this you can write this as give me a second. You could write this as just 1. Now put sigma in both sides. Sigma ln n over n. N goes from 1 to infinity greater. Sigma n goes from 1 to infinity 1. All right. Now you have to check whether this is convergent. You have to show this is convergent. If this is convergent, then that is convergent. If this is divergent, you can't tell anything about that. That is the theorem. Unfortunately, you see that this series diverges. If you just add ones, you will get infinity. If you add number 1 infinitely many times, this is infinity, so that diverges. All right. Thus, the test failed. Okay, so sorry. So it's a sad mood. All right, the sad mood. The test fails. This is let's say this is try 1. Now let's go for the try 2. Now let's go for try 2. In try 2, what we are trying is just something less than an. Try something less than an. Already we have tried this thing greater than an. Now let's try something less than an. All right. For that, what I would do, I will just arrange this series. This is the given series to me. See, that's the given series. So I'm going to just make a small arrangement with that series. I'm going to write first three terms of this series. Okay, I'm going to write first three terms. The first term is ln1 over 1. The second term is ln2 over 2. The third term and the rest of the term I write like this: n equals 3 to infinity ln n over n. All right. So what I have done is I have expanded and removed the first term and the second term. You know ln1 is 0, so you can write this as ln2 over 2 plus sigma n goes from 3 to infinity ln n over n. All right. Now let me analyze this series. Let me analyze that series. Well, first of all, let me number this equation as equation number 1, and then I'm going to analyze this series. All right. All right, so go forward. Before analyzing this series, I'm trying to make an inequality which has this ln over n part. I'm going to make an inequality that has this part. I will explain later why I do that. Okay, first let me make that inequality. So you know this fact. You know ln 3 greater than 1. Okay, ln 3 greater than 1. Now I'm going to show this. This is, you learn this in Calc 1. Let me draw a small plot and show you that. Let's consider this is 1, 2, 3, and then just consider this is ln n. Okay, you know this. ln1 is 0, so the graph goes through that point, and ln2 may be somewhere here, and ln3 may be somewhere there. Okay, so this graph goes like this. That is the logarithm graph, you know that. And this is ln 2, and this is ln 3. All right. Now this is ln 3, which is right here. And then just compute ln 3. Okay, actually ln 3 is you can use the calculator and compute this. If I use the calculator to compute ln 3, which is give me a second, I will compute that. Which is 1.0, you can say 0.99, and then if you compute ln2, which is 0.693, and you can see 1 is in between these two values. Okay, 1 is in between these two values. You could say 1 is right here. Okay, so now you can see ln3 is ln3 is greater than 1. Okay, so this is obvious. Okay, let me mark that in green. This is obvious. You can refer to these values. ln3 is greater than 1. And not only that, when, give me a second. When n is greater than 3, ln n is greater than 1. As an example, this is 3, ln 3 is greater than 1. This is 4, this is ln 4, which is also greater than 1. This is 5, ln 5 is also greater than 1. That means, give me a second. That means ln n is greater than 1 for all n greater than 3. When n is greater than 3, all the logarithm values are greater than 1. Alright? When n is greater than 3, all the logarithm values are greater than 1. So that is very clear to you now. This is actually Calc 1 work. Alright, so just start the inequality from here. I have written down ln n greater than 1 for n greater than 3. Now what I'm going to do is I'm going to divide both sides by n. So I'm going to write ln n divided by n, that alright, and you can see this part is already there. So that's why I just did this everything from the beginning. Okay, because I just wanted to make that part over here, which is equal to that. Alright, now I have this inequality. What happen if sum of that what happen if sum of this diverges? If sum of this diverges, the summation of that should also diverge. Okay, let me write that down. We have to show that sigma n goes from 1 to infinity. Let me make it n goes from 3 to infinity, because we are starting from 3. N goes from 3 to infinity, that diverges. Okay, if the smaller series diverges, the bigger series should diverge too. Alright, how do you show this diverges? Okay, now again we are going back to the P series. We are again going back to this P series. We know that sigma n goes from 3 to infinity 1 over n diverges since it is a P series with P equals 1. So this power is actually P. This is n to the power 1. So this power 1 is actually P. N to the power 1 is actually P. So it is a P series with P equals 1. Okay, if you can remember what the P series is, you can just refer the previous day note. All right. Okay, now let me write things like this. Since sigma n goes from 3 to infinity, that diverges this series also diverges. By the direct comparison test. Okay, by the direct comparison test. Now you see this thing, this series, I'm sorry, give me a second. This series is actually given right here. This equals that, they are same. Okay, now you know that this series diverges. That means this green color circle is infinity. You add some real number to infinity, but it is still infinity. Okay, you add real number to infinity, it is still infinity. That means this is infinity. Okay, that means the given series is divergent. Okay, so let me write that. By 1 is this equation. By 1 we say sigma n goes from 1 to infinity, ln n over n diverges. Okay, so that is the solution. Okay, that's end of the section. Here we discuss two problems. The first problem is easy one. The first example was easy one. But the second example was little harder because you had to try two cases. First you were trying to make something greater than the given series, and then we tried making something smaller than the given series. All right, so this part of the comparison test is called the direct comparison test. In the next day we are going to learn limit comparison test. Thank you very much.